Okay, so we will talk about example of another divide and conquer technique, which is basically QuickSort. So it is basically a sorting algorithm where we have a we need to sort a array of. So this is the input, we have given n numbers, the numbers are in array, what could be any other form. Now we need to sort this number. So this is the sorting algorithm, and we have seen so far two sorting algorithm like insertion sort, merge sort. So merge sort is one of the one of the example of divide and conquer technique. Now QuickSort is another divide and another example of divide and conquer technique. So it has basically 3 steps. So every divide and conquer technique has 3 steps. We have given a problem of size n, we divide the problem into sub problems of lesser size, that is the divide step, and in the conquer step we conquer the sub problem by recursively solving them, and then once we have we got the solution of these sub problems, then we combine the solution to get the solution of the whole problem. So that is the divide and conquer technique. So in merge sort, what we did in merge sort, we have a array of size n, we need to sort, we divide into 2 part, half, we then that is the divide step. So merge sort divide step is very simple, and the conquer step we sort this subarray, we sort this subarray by recursively calling the same merge sort. Then once we have the solution of these two subarray, then this is sorted and this is sorted, then we call the merge subroutine. So this will take a array, extra auxiliary array. So it compare the minimum with minimum, whichever is the minimum it will output that next minimum like this. So this is the merge subroutine. So that is the combine step in the merge sort. So merge sort combine step is crucial than the divide step. Divide step is very straightforward, we are going to the middle of the array, we divide the array into 2 parts, that is it, that is the divide step. But combine step we have a merge subroutine, and that is of linear time, and for that we need to have a extra storage. So that is why merge sort is not a in place sort. For merge sort we need a extra storage. So now we talk about QuickSort, which is a in place sorting algorithm and which is also divide and conquer technique. So in the divide, first step is divide step. In the divide step, what we are doing? We divide, this is the divide step. Basically, we partition the array. We have given an array of size n initially. We partition the array into two subarrays based on a pivot element x. We called an element, among this anyone could be a pivot, but for our partition this is done by a subroutine which is called partition. So based on a pivot element x, which is basically an element from this array, such that all the elements in the left subarray are less than x or less than equal to x, and then all the elements are in the right subarray are greater than x. All the elements in the right subarray. Okay. So basically we have, this is our given array. So what we are doing, and this is done by a subroutine which is called partition. This is done by a subroutine which is called partition. Okay. So basically, so we choose, so among this element we choose one element as a pivot. So x is pivot element, For our partition algorithm, we take first element as a pivot, but pivot could be any of this, any of the element from the given array. So, we choose this pivot. Now, in this divide step, what we are doing, this partition algorithm, partition subroutine, it is partitioning the array into two parts. It is putting the pivot in its correct position in the sense. So, if we sort this array, the position of x where it should be in the sorted array, that is called correct position. So, x will be sitting in its correct position and all the elements in the left sub array will be less than x. If there are repetition less than or equal to x, all the elements are if there are all the elements are distinct, then this will be strictly less than x, this will be greater than x. So, this is we want in our this divide step. So, they need not be sorted. Suppose for example, if we have an array like this 6, 7, 5, 8, I say 10, 8, 2, 4, 3, 9. Suppose this is our given array, this is the input, okay, this is our given array say. Now, suppose we call the partition algorithm on this array by choosing this 6 as a pivot. So, our x is 6 as a pivot. Now, we want this divide step should give us, so it should put the 6 over somewhere here. So, this is 6 and it should partition this array into two parts. All the elements less than 6 should be in the left sub array. So, who are the less than 6? So, 2, 4, 3 should be in the left sub array and all the element greater than 6 will be in the right sub array. Who are the greater, sorry, 5 is also there. So, 5, 2, 4, 6, these are the element less than 6 and 7, 10, 8, 9. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So, this is the output after the partition call on this array. So, you want only this. This is, if you see, this is not sorted, this is not sorted, but only thing 6 is in correct position. So, we put the 6 in correct position. That means, if we sort this array where this pivot should be x is in correct position. So, this is the subroutine partition will do. So, it will just divide the array into two part. The left sub array, all the elements in the left sub array will be less than x, all the elements will be right sub array will be greater than x. So, this is the job of the partition algorithm and this is the divide step. Okay. Now, what is the concat step then? So, now we have two sub arrays. Now, concat step is what? Now, we have to sort this sub array by recursively calling the same QuickSort. So, we recursively sort both the array, both the sub arrays. This is the concat step. That means, now again we need to call this QuickSort here, QuickSort here. Then in that QuickSort call again we need to choose this as a pivot. If we choose first element as a pivot, then again it will partition into sub array like this. So, we continue. And then what is the combined step? So, in concat step, once we call the concat step, then this after the completion of the concat step, this is sorted array, this is sorted sub array and 6 is in correct position. So, what is the job remaining? What is the combined step? What need to combine? Nothing has left, all done, all done. So, combined step is nothing, we are done, all done, it is nothing has left. Okay. So, that is the combined step. So, we have this the combined step is trivial, nothing has left. Now, the idea is to have a partition subroutine in linear time, that is the key idea of the QuickSort. We need to have a partition algorithm in linear time. So, we will discuss that in a moment, that what is the partition code, what is the pseudo code for partition, which will give us the runtime linear. So, that is the key point of the QuickSort. And if you just see the QuickSort, if you compare the QuickSort with merge-sort, the divide step was trivial. We just go into the middle of the array and we divide into two parts, and concat step we sort this part, we sort this part, and the combined step was the merge subroutine. So, combined step was more than the divide step in the merge sort, but here divide step is more than the combined. Combined is nothing in the QuickSort. Okay. So, this is the divide and conquer technique for QuickSort. Now, we talk about the partition algorithm. So, this partition subroutine, how this array will be divided into two subarrays such that all the elements which are less than x will go to the left subarray, all the elements which are greater than x will go to the right subarray. So, that is the, and that should be done in linear time. Okay. So, that is the partition code. So, let us just write the partition code, pseudo code for partition. So, it is basically, so partition, it is taking an array which is say p to q. So, initially it will take 1 to n, but again on the sub array we are calling the partition. So, it will be index won't be 1 to n for throughout the subsequent call. So, index will change. So, that is why you are taking the general index. So, initially p is 1, q is n. So, we have a array which is A, which is starting from p to q. This is a input of this partition. Okay. So, for our version of the partition, we are taking first element as a pivot. So, AP. So, whatever the value over here, this we are taking as pivot. Okay. And what we want from this? We want at the end of this code, it should partition this array into two parts such that x will be putting somewhere here and this index is r, such that all the elements over here will be less than x, all the elements here will be greater than x if they are distinct. Otherwise, if there are some equal element, which will be, you can use this. So, this is what you want from our partition algorithm. So, let us write the code. So, you start with 2 index, I is p, and we have a for loop for j is equal to p plus 1 to q. Okay. So, j is equal to p plus 1 to q, and so this is a loop. Now, if we to write a code, it will help us if we know what is the loop invariant we are looking for in this, then it will help us to write a code. Every algorithm, every pseudo code, if we know what we are looking for, then it will help us to write the code. So, what is the loop invariant here we are looking for? So, we are looking for this is the loop invariant. So, I is pointing somewhere here and j is pointing somewhere here. Okay. Now, what we want? The loop invariant is all the elements here would be less than x, less than equal to or less than if there are identical elements, and all the elements here will be greater than x. This we want, all the element here should be greater than x, and this is yet to decide. So, that is the invariant. So, what is the initial step? Initial step is initially I is pointing here and j is pointing here, and initially everything is yet to decide. So, that is the initial condition, nothing is decided yet. So, that has to decide, that is the initial step. Okay. But at some point of time this will be the situation. Okay. So, we take this. So, now if this one j is varying, now if this is our aj, now if aj is greater than x, suppose aj is greater than x, then we can increase j by 1, and that will be taken care by this for loop. This is a for loop in j. So, it will automatically increase. if you do not do anything. So, if aj, if this is greater than x, then cool, no need to do anything here. So, it will be just automatically increase j by 1. Now, the problem is, if this guy, if this is less than x, if this is less than x, suppose x is 6, say, suppose x is 6 and suppose this is say 4 for example. So, this is less than x, now we cannot just increase j by 1. So, we need to do something. So, that what we need to do, that we have to think. So, we cannot just increase j if this is, say this is less than, so this is our aj. So, if this, then we have a problem, then we have a problem, then that problem how we can tackle. So, then we cannot just increase j by 1, we cannot just increase j to this point by this for loop. In that case, we are not violating our invariant. So, for that what we want? We know we want to exchange this with somebody which is greater than x. So, what we know? We know the element which is sitting here, that I plus 1, this is I plus 1 element. We know this element which is sitting here is greater than x. Now, if we just exchange this and this, and if we increase I by I plus 1, then we are through. Then also we have this was I. Now, now this is j. Now, this is less than x and this is greater than x, we know. Now, if we increase I by 1 and if we exchange this guy with this, now this x is coming here and now this x is greater than x, and now this guy is greater than x and this is less than x, then we are through. Then still the loop invariant is there. The loop invariant means the point where I up to I. So, this is the loop invariant we want. So, if this is the I, then all the elements here is less than x. If this is j, all the elements here will be greater than x. This is the way we will handle this situation. If the aj is less than x, if aj is greater than x, no need to do anything. So, that we have to write. Do if aj is less than x. If aj is less than x, then we have to do this. What we do? We increase I by 1. So, I will be I plus 1, we increase I by 1. Now, the ai is some element which is greater than x. Now, we exchange ai with aj. Now, we exchange ai with aj. That is it. Now, we exchange ai with aj. Okay, exchange. So, if we exchange ai with aj, then peacefully we can increase j by this, that will be taken care by this for loop. Okay. So, this is 5, this is 6 and then, so this is the loop and this will do for until the j exhaust, and then finally, we have 7. So, after exhausting this loop, what we do? We will put the pivot element in its correct position. So, that will be done. So, j exhaust, now I will be pointing somewhere. So, now where I is pointing, that guy is less than equal to x. So, now we exchange ap with ai, ap with ai and we returned ai. So, that is the, that will give us the position where we have put it x. So, this will exhaust, so j will exhaust. So, j will exhaust. So, j is gone and now I is pointing somewhere here and all the elements over here is less than equal to x. Okay. So, now j is gone, j loop is exhaust. So, now we put it here. So, x will be putting here. So, now we return this is our I, we return this value of this element to indicate that where we kept the pivot element, so that it will identify the left subarray, right subarray. Because again in concat step, this is only the divide step. Again in concat step, we have to call the QuickSort on this subarray, on this subarray. So, if we can identify, to identify the left subarray, we need to have the index where we kept the x. So, that is the point, that is why we need to return I. unless we return I, we do not know where we kept x. Then we have to call this QuickSort on this part, we have to call this QuickSort on this part. So, this is the pseudo code for partition algorithm. Now, let us have an example, then it will be more clear. Let us execute this code on an example, on an input. So, say let us take an input, say example of partition. Okay, suppose we have given this input 6, 10, 13, 5, 8, 3, 2, 11. Suppose this is our input and we want to execute this partition algorithm on this input. So, okay, so this is our array. So, this is A P to Q. Now, we choose this as a pivot. So, our pivot is x is 6. So, this is our pivot. Okay. Now, we point this to be I, this is P plus P, and we start our J loop from here. And every time we increase J by 1 by this for loop. Now, if we now compare, and what we want? We want that this is the loop invariant we want. We want wherever this I is pointing and wherever J is pointing, we want all the elements should be less than x, all the elements should be greater than x, and this is yet to decide. Okay. So, this is the loop invariant we want. So, now we check this, this is our now AI. Now, if AI is greater than x, then no need to do anything, we will not enter into this loop. Then the J will be increased by 1 just by this for loop. Now, J is pointing here. Now, again the AJ is 13, which is greater than x, x is 6. So, again we increase this by 1. So, this is basically J is now pointing here. Okay. Now, if J is pointing here, now this is our AJ. Okay, this is our AJ. Now, we compare this with 6. Now, this is less than. Now, we cannot just increase J by 1, then that will violate our invariant. Now, what to do now? Now, we know that the person who is sitting here, the element which is sitting here is greater than. So, we will just increase I by 1 and we exchange this with this. So, this will be like this. So, 5 will come here, 13, 10, then 8, 3, 2, 11, and now I is pointing here and J is just this exchange. Now, J will be increased by this. Now, J is pointing 8. Okay. So, now what to do? Now, again we compare AJ with 6. Now, AJ is greater than. So, we can peacefully increase AJ by 1 and that will be taken care by this for loop. So, now J has increased by this. Now, AJ is 3. Now, we got a problem. Now, AJ is 3, which is less than pivot element 6. Now, we need to do something. So, what is that? We increase I by 1 and we know the element sitting over here is less than. So, we just exchange this and this. So, this will give us 5, 6. So, this is 3 and 10, 8. So, 13 will be going there, 11. Okay. Now, I is pointing this 3 and now J is pointing this. So, 3 and 13 has exchanged, J is pointing this 2. Okay. So, this is the situation now. Now, again AJ is less than pivot. Now, again we have to exchange this. So, we know the element sitting over here is greater than. So, I is increased by this and we exchange this and this. So, now this is the 5, 3. So, 2 will come here, 8, 13, 10 will go there and 11. So, now I is pointing this 2 and J is pointing here. Now, if you see all the elements up to I, these are less than equal to x, and all the elements up to J, these are greater than equal to x. So, this is the loop invariant we want. for our this partition code. This is exactly it. This is the loop invariant we want for our partition code, and then we increase this j by 1. So, j will be pointing this. Now, this is 11. So, nothing to be done. So, this is gone. So, j exhaust. So, j loop is gone. So, we cover everything. Okay. So, now this is our I. So, I is basically this. So, this is index if we write 1, 2, 3, 4, 5, 6, 7, 8. So, this is basically 4. Now, I is 4. Now, what we do? We have to put this pivot in its correct position. So, we exchange this AP with AI. So, we exchange these two 6 and 2. We exchange these two, then this will be 2 and this will be 6, and we return I. So, we return 4. So, this will return us like this. So, this will return this is 6 will be sitting here, and this is index is 4, and all the element here is 2, 5, 3 and 8, 13, 10, 11, and this is the index we have to return to identify the left subarray, and this is the right subarray. Okay. So, this I is the index, this is say R. So, this is the I. So, this 4 is returned. So, the partition will return the element 4. Okay. So, this is the partition algorithm. Now, what is the time complexity of this algorithm? Because it is just have a for loop in J. So, just if we just erase that. So, just if we write the partition. So, this is basically just quickly I will write it. So, this is the for j is equal to p plus 1 to q. So, you want to find the time complexity for this. Okay. So, if aj is less than x, then what we are doing? We are doing I is equal to I plus 1, and we exchange ai with aj, that is it. So, that will be 5, 4, 5, 6, and then after this we are just exchanging AP with AI, and we returned AI. Okay. Now, we want to find the time complexity for this. What is the time complexity for this? So, this will take constant time, this will take also constant time. Okay. Now, this is a loop in size n. Okay, because we are assuming the order of the size of this array is n, q minus p is n. Okay, if we have a input of size n, then what is the time complexity? So, now this is n. Now, whatever we are doing here, these are all constant, because we do not care about how much time it is taking by this checking less than then this assignment, because we want this analysis to be machine independent analysis. So, that is why we need to bring the asymptotic notation. Maybe in our computer, in our brand new machine, this will take maybe microsecond, but if you have a old computer, it is taking more time. So, we do not bother about that. That is why these are all constant time. We are taking theta of 1 time for this. So, this is again theta of 1, theta of 1. So, this is basically theta of n. This is a linear time algorithm. So, this is a linear time algorithm for this partition if we have a given array of size n. Now, we will talk about QuickSort, how we will use this partition in the QuickSort algorithm. So, that we will discuss in the next class. Thank you.